Hello everyone. So today we'll be discussing the Hamiltonian path or cycle algorithm, right? So this is going to be the last algorithm in the graph-based algorithms playlist. So this is going to be special. So we'll be completing this one graph-based algorithms with this particular topic, yeah, or with this particular algo, right? So previously we had discussed on the this one topic Eulerian path or circuit algorithm. Now let's move on with the Hamiltonian path or cycle algorithm. Yeah, let's see the definition part. Let's see what the definition part states here, right? An Hamiltonian path is a graph. This one in a graph is a path that visits every vertex exactly once. Yeah, and Hamiltonian path in a graph is a path that visits every vertex exactly once. Yeah. Now, an Hamiltonian, this one, a Hamiltonian cycle or the circuit is a Hamiltonian path that starts and it ends at the same vertex. That starts at this one. Hamiltonian cycle is nothing but this one. It is a Hamiltonian path that starts and ends at the same vertex, forming a cycle, right? So now let's go with the explanation. So the Hamiltonian path problem, this one, the Hamiltonian path problem is a classic NP complete problem. NP in the sense non-deterministic polynomial time, right? So non-deterministic polynomial time in the sense, see, we make use of this term. Usually, you would have heard this term whenever the problem is very tough, right? So usually we make use of it. So this is complete an NP problem, and we cannot solve this one. In particular, this one, what do we call time? We cannot verify the solution. This one in particular time. Those kind of in those kind of situations, if you want to express that the problem is very tough or very hard, right? The problem is not solvable. If you think in that way, we use this term usually NP based problem or something like that, right? So usually I have used it in that way. So it is NP, nothing but NP. This one. NP stands for non-deterministic polynomial time, right? So if someone gives us the possible answer, right, and then if you are able to verify it quickly, so that we call it and this one, we can verify that one in the polynomial time, so that is fine. If suppose if we say, if someone is saying, or if we say it is hard as any problem in the NP, means it means that if we could solve this one quickly, uh, we could solve all the NP problems quickly as well, right? NP problems are this one. NP complete problems are the hardest problems among the NP problems, right? NP problems, this one, NP complete problems are hardest problems among the NP problems, nothing but the non-deterministic non-deterministic polynomial time. Non-deterministic polynomial time. Yeah. So the Hamiltonian problem is classic NP complete problem, right? So NP complete problems are again the hardest problems among the NP problems. Just remember this. The Hamiltonian path problem is a classic NP complete problem in the graph theory, right? What is our goal here? Our goal is to determine whether such a path or the cycle exists on the given graph or not, in the given graph or not. In Hamiltonian path, let's move on with the points. Yeah, let's move on with the further points here, important points. In Hamiltonian path, we just need to visit all the vertices once. Yeah, in Hamiltonian path, we just need to visit all the vertices once. In Hamiltonian cycle, we must also return to the starting vertex. Again, let me tell you this one. In Hamiltonian path, we just need to visit all the vertices once, right? In Hamiltonian path, we need to visit all the vertices once. In Hamiltonian cycle, we must also return to the starting vertex. We must also return to the starting vertex, right? So that causes loop, which is called a cycle basically. Since the problem is NP complete or the non-deterministic polynomial time complete, no polynomial time solution exists for the general graphs for this particular one. Yeah, whatever I explained, just listen to this carefully, right? Don't worry about the this one output, this one, and output is not everything. So just listen to whatever we understand, right? So I mean, just listen to whatever I say. This one basically about the algorithm. Yeah, whatever we discuss, right? Hence we usually solve it using backtracking, right? Since the problem is NP complete, no polynomial time solution exists for the general graphs, and also hence we usually solve it using the backtracking, trying all basically, right? Backtracking we know, Yeah, what the term backtracking, I don't have to explain you guys, right? Backtracking, trying all. This is fine. Trying every combination, right? Possible paths and checking if satisfy the condition. Trying all the possible paths and checking if one satisfies the condition, right? The conditions, right? So this is it for the explanation part. The same thing, let's try to implement or articulate in the form of code or the algorithm by making use of the Python programming language. Yeah. Now let's do one thing. Let's start writing the this one code. Just give me a second here. Did I miss anything? All right. First, let's define the function to check if the current vertex can be added or not. Nothing but we are checking whether it is valid or not, right? So I'll just go with def here. I'll name the function is valid, right? So this one will be v comma graph. Also, let's go with a path also and positions as well. Now, if this vertex is not connected to the previous one, then it's said to be invalid. So I can just go in this way. If graph of this one, what do we call path, path of this one, position minus one, position minus one, then let me go with a v. So this one, let me we are checking the value is equivalent to 0, right? So if it is 0, meaning if the particular vertex is not connected to the previous one, then it's said to be invalid, right? So let me return this one, Boolean value false. It is as it is invalid. This is fine, man. Now, what if the vertex has already been included in the path? Then also it's invalid. Now let's write the this one if condition. If v in path, if v in path, so here if v in path, then here then also we have to return false as it is invalid, right? So this is fine. Next step, else we have to return true. Else we have to return true. So let me go with true here. This is fine. We are done with the first step. Next step is let's go with a recursive function to find the Hamiltonian cycle. We are going with we are dealing with the Hamiltonian cycle. Just remember this one. Yeah. Now I'll just give here def Hamiltonian this one a here Hamiltonian cycle we are going with, right? So I'll just name this one Hamiltonian cycle until. Yeah, this is fine, man. I need the parameters graph, path, as well as the position, as well as the position. Yeah. Now let's go with the base case, nothing but if all the vertices are in the path, if all the vertices are in the path, so I'll just go with position equals length of graph. If all the vertices are in the path, if position equals length of the graph, then what we will do here, we'll check if there is an edge from the last to the first vertex, meaning I'll just go with return graph of, let me go with the path of this one, position minus one. This is fine. Yep. Now me go with path of 0 as well. Yep. So let me assign this one. We are checking this one. We are checking, right? Yeah, to 1 actually. Yeah, we are just checking if there is an edge from the last to the first vertex, right? So this is fine, man. Now what we need to do, let's try the different vertices as the next candidate. Let's try the different vertices as the next candidate. So let's move on with the for loop here. So I'll just go with for v in range. What's the range actually? We have to go with from 1 to this one, the length of the total graph, right? So I'll just go with length of the graph. So this is fine. So within the for loop, what let's go with the is valid that we have written already. Is valid function, right? Is valid function. Let me pass the parameter here. So this one has to be v. It consists of the parameters v, graph, path, path as well as the position, right? So this one, let me copy this one. Copy this one as well. Yeah, this is fine, man. Now let's do one thing. Path of position. This is equivalent to the v, and also if Hamiltonian cycle until. So let's go with let's recurse in simple terms. If Hamiltonian cycle until, so I'll just go with the graph as well as path as well as position plus 1 here. Position plus 1, then we have to return true in that case. So let me give here return true, right? So this is fine. The next step is we have to backtrack if adding the vertex v doesn't lead to the solution. So I'll just go with path of position. Let me assign this one to the -1. Else else let's return false here. Else let's return false here. So I'll just go with return false. Yeah, we are done with the coding part. Now, what is the next step? So we have to write the function to find and print the Hamiltonian cycle, right? So I'll just go with def here. Hmm, let me go with 1 second. So this one, let me keep this one as small exception. So I'll just copy here Hamiltonian cycle until here. Hamiltonian cycle. This remains same actually. Yeah. So let me pass the graph. I need the parameter graph within the function. So this is fine. This is fine. Yeah. Now let's do one thing. Mm, let me assign this one to the length of the graph so that we can make use of the variable n instead. Right. So this is fine. So path. Let me initialize this one to -1 into n. This is fine. Finally, let's start at the vertex 0, meaning let me initialize path 0 to 0 itself. Yep, this is fine, man. We are just starting at the vertex 0. Now this is fine. Now, if not, so I'll just go with if not Hamiltonian cycle until. So this one, let me go with graph, this one path as well as the 1. This is fine. So now what shall we do? Let's print something. Let's print something for the interactive purpose, right? So I'll just go with print. So this one is no Hamiltonian cycle exists, right? No Hamiltonian cycle exists, right? So this is fine. Then let's return false. Return false. This is fine. Yep. What if we have found, then we have to print the path, right? So let's make use of the print here. So I'll just go with Hamiltonian, this one. So we call cycle exists, right? So this is fine. Then let's print something here. Print, let me go with the path, uh, path of 0, path of 0, right? Finally, let's return true. Let's return true, right? So this is fine. Let's return true. Now we are done with the 3 steps. Now let's do one thing. We are done with the algorithm part one. So let's consider the example graph, or let's go with the adjacency matrix, right? Let's go with the adjacency matrix. I'll just consider this one from the Google itself. Let me copy paste this one. Just give me a second here. So here, so this one, whatever the example that I've considered. So this one, basically, this is just the example graph one. So sorry, this was not the adjacency list. This is the adjacency matrix, right? So we're not considering the adjacency list here. We are considering the adjacency matrix. So this is nothing but we are just calling the function Hamiltonian cycle here. So I have passed the graph, this one, adjacency matrix, right? I've passed this one. This is fine. So before checking the or before running the code, let me explain the algorithm once so that we don't forget. Yeah. Now first we have went with the isValid function here. So what it does, it checks two conditions. Just remember this: whether the current vertex is connected to the previous vertex or not, and not already included in the path. So whether the current vertex is connected to the previous vertex and not already included in the path. So these two conditions will be checked by isValid function, right? So next let's come to the Hamiltonian, this one, cycle until, right? So this one, we are making use of the recursion here, right? So it recursively tries to add each vertex to the path. If we reach a path containing all the vertices, then we will check if the last vertex connects back to the first or not within the Hamiltonian cycle until function, right? So this is fine, I believe. Next, let's move on with the Hamiltonian cycle. This one. So basically what it does, it initializes the path and triggers recursion. It initializes the path and triggers recursion, right? So it prints the Hamiltonian cycle if one exists, otherwise it reports none. Otherwise it reports none. Yeah. The graph is represented as an adjacency matrix. The graph is represented as an adjacency matrix. Finally, the function prints the valid Hamiltonian cycle. Finally, the function prints the valid Hamiltonian cycle. Yeah, this is fine, I believe. Yep. Now, this one adjacency matrix I was speaking of. Finally, this one, the function prints the Hamiltonian cycle. We have complete idea on the algorithm now. Let's run the code. So before running the this one, whatever the code that we have written, so what is the output that we need to get here basically? So let's discuss the output and then let's discuss the this one. Then let me write the this one. What do we call? Let me run the code. Just give me a second here. 1 second. Yeah. So now the output here that we need to get here is Hamiltonian cycle exists basically. Hamiltonian cycle exists along with this one. Hamiltonian cycle exists along with this one. The cycle is that we need to get here is this one. 1, 2, 0, 1, 2, 4, 3, and 0. 0, 1, 2, this one, 4, 3, 0. Right. So how why we will get 0, 1, 2, 4, 3, 0 here? See, the printed sequence basically it shows the order of vertices forming the Hamiltonian cycle. So here 0, 1, 2, 4, 3, 0 for the input that we have considered. This means actually the output how we got. We will start at the vertex 0. We'll start at the vertex 0. Then we will visit the vertex 1. Then we will visit the vertex 1 followed by the 1. Then we will visit the vertex 2. Then we will visit the vertex 2. Then we will visit the vertex 4. From 2 we will visit the vertex 4. Then from 4 we will visit the vertex 5. Yeah. Sorry, from 4 we will visit the vertex 3, right? So from 4 we'll visit the vertex 3. So this is the uh, basically this forms the cycle. Yeah, we are starting at the vertex 0. We are visiting this one from 1 to 2 to 4, this one to 3 basically. Yeah, from 1 to 2 to 4 to 3, right? We are starting at the vertex 0 actually. Yeah, and we will return to 0 completing the cycle. So this one I should have written, sorry, this one don't consider this one here. So instead this one consider here. So yeah, it returns to 0 itself in the sense. So yeah, we have sorry, I got confused here. This one we have to consider from here. We are going for the loop, right? So this one again it returns to 0 actually. Yeah, from 3 to 0. 0, 1, 2, 4, 3, 0. Sorry, I got confused. Yeah. So here we are starting at the vertex 0. We are starting at the vertex 0, then 0 to 1, 1 to 2, 2 to 4, and 4 to 3. And then finally we return 0, completing the cycle. So this forms a cycle basically. Yeah, this forms the cycle. Each vertex is visited exactly once. Each vertex here, see, each vertex is visited exactly once, right? And the last vertex connects back to the first, this one. Last vertex connects back to the so this one. So this one we have to give 0 here actually. From here we are visiting the this is fine. The last vertex connects back to the first, fulfilling the Hamiltonian cycle conditions actually, right? Yeah. So this is the reason we have to get the output 0, 1, 2, 4, 3, 0, right? For this one. So this is NP complete problem, right? So this is fine, man. Yeah. Fulfilling the Hamiltonian cycle conditions actually. Yeah. The out. Let's run the code. Just come here. Let me give Control J. Give clear screen here. Python followed by filename.py. Yeah, so we are getting the output 0, 1, 2, 4, 3, 0. Hamiltonian cycle exists and the path they have given here 0, 1, 2, 4, 3, 0. The desired output that we are getting, right? So this is absolutely correct. Whatever the code that we have written works absolutely correct. Now, as we are completely done with the Hamiltonian path or cycle algo, let me summarize whatever we have learned so far, right? So the first point here, just try to remember these 4 to 5 points. This is very important. Hamiltonian path. So this visits all the vertices exactly once. Hamiltonian path, what it does, it visits all the vertices exactly once. All the vertices exactly once. This is one thing. And what about the Hamiltonian cycle? Hamiltonian cycle, this one, Hamiltonian path that returns to the starting vertex. That returns to the starting vertex, right? So that's what it did. That's what it did actually, this one cycle. 0, 1, 2, 3, 0, 1, 2, 4, 3, again 0, right? From 0, again we went to the same vertex, if you remember. Right? That's what I showed actually by considering the graph. So Hamiltonian cycle, so Hamiltonian path that returns to the start vertex, nothing but the Hamiltonian cycle. So the third part here would be the algorithm uses backtracking. So it uses backtracking, right? So Hamiltonian, this one, what do we call? Path or the cycle algorithm, it uses backtracking to try all the vertex combinations, right? So this is fine. These two, this one, the next 2 points are very important. Just listen to this. It's a NP complete problem. Yeah, non-deterministic polynomial time complete problem. So this is efficient only for the small graphs. It is efficient only for the small graphs, right? So just remember this one. It is efficient only for the small graphs, right? So the final one is, so this is, let's discuss the use cases. It is useful for the path optimization problem, like traveling salesman problem. You would have come across the traveling salesman problem quite often in the lead code. So this is quite this one. This is useful for the, sorry, this is useful for the path optimization problems like traveling salesman problem. There we will be making use of the Hamiltonian path or the cycle algorithm. So yeah, this is one of the use cases, right? So these are some of the important points I wanted to discuss regarding the Hamiltonian path or cycle algorithm. Yeah. So we are done with the graph-based algorithms today. We have hit the milestone, right? So we are done with the graph-based algorithms today. Next, what we'll be doing? So we will be continuing with the this one, dynamic programming algorithms, DP algorithms, right? Next, we'll be continuing with the dynamic programming algorithms. So I'll just read out what are the algorithms that we'll be discussing in the this one, discussing in within the DP algorithms playlist, right? First one will be longest common subsequence. This is one of the important ones. Longest increasing subsequence, then matrix chain multiplication. This is one of the important algo. And 0, 1 knapsack problem, very important one. Unbounded knapsack. This is one of the very important algorithms as well. Next one we'll be discussing on this one, subset sum or the partition problem. So this is one of the important algo as well. Coin change algorithm. This is one of the important one. Rod cutting problem or algorithm. This is one of the important ones. So next, Bell numbers or the Catalan numbers. This one DP. That is also one of the important algorithms. Floyd-Warshall algorithm. So which is completely based on the DP. This is important. Tree DP. We will be going with a digit DP algorithm. We'll be going with a bit mask. This one DP algorithm, and finally DP on the DAG. DAG nothing but the directed. This one direct acyclic graph, right? So these are some of the algorithms that we'll be going with. Total we'll be going with, 1 second, uh 14 algorithms, I believe. Yeah, total will be going with a 14 algorithms for that within the DP based algorithms. Yeah. Now we are done with the this one, graph based algorithms or the Hamiltonian path cycle algorithm. Let's finish it off with this particular algorithm. For now, this is it. Thanks for watching, guys.